So let me briefly introduce you to the basics of the physics behind nuclear power. Now this graph shows all possible atomic nuclei. So nuclei made of neutrons and protons bound together by the strong interaction, and you can plot them by the number of neutrons along the bottom and the number of protons up the side. And this is all the ones that have currently been found by humanity. Let's zoom in to see in more detail. The black ones here are the ones which are stable, so they will last a long time. So for example, down here is hydrogen, helium-4, and so on. And the ones in various colours are unstable, so they won't last for long. They will at some point break down, and the colour codes how they break down. So for example, emitting a neutron or emitting an electron or a positron or a proton or something like that. And you can see the stable ones tend to be in a diagonal line with roughly the same number of neutrons and protons. I won't explain why that's the case, but if you do a nuclear science course you can learn all about that. What you can see is that any particular horizontal row has a certain number of protons. It's a particular element. So for example, helium has 2 protons. But there's a bunch of different isotopes. These have the same number of protons and also hence the same number of electrons orbiting much further out, but they're different numbers of neutrons. So if you take up here carbon, the most common isotope of carbon is carbon-12. It's written with a little raised 12 in front of the C. But carbon-13 with 1 extra neutron is also stable, and carbon-14 that still exists. It's produced by cosmic rays bombarding the upper atmosphere and lasts a few thousand years. So for many elements you get different isotopes which have different properties, and that's going to be crucial for large amounts of nuclear physics. So this is just saying all that. The crucial thing about different isotopes is that while the nucleus has different numbers of neutrons, that doesn't affect the chemistry, because chemistry is controlled by electrons bonding with other electrons in various ways, and so different isotopes of the same element are chemically identical. There is no chemical reaction that can separate out carbon-12 from carbon-13. It just can't be done. You have to actually use some sort of weight method to separate them out, and that's also going to be crucial. Now, this is a graph of the binding energy per nucleon. Nucleon is a proton or a neutron, so this is how much energy it has by virtue of being near other things. And what you can see is the most stable element with the most binding energy is iron, 56. And the graph curves down to both sides. What this means is, if you've got any element that's further down, if you can turn, for example, hydrogen into iron, you're going to liberate quite a lot of energy in the process. So that's going to generate a lot of electricity or whatever it might be. Likewise, if you convert uranium into iron, it's not as much energy, it's only this height here compared to that enormous height over here, but still you can liberate some energy. Whereas if you've got a massive iron, there's nothing you can do. You can't get any nuclear energy out of iron, it's just at its most stable point. So these are the two forms of nuclear energy, converting really heavy elements down towards iron by nuclear fission, which is where these really heavy elements split into smaller, more stable lumps, or fusion, which powers the sun, taking these light elements like hydrogen or helium and merging them together until you form something nice and stable. So fusion generates more energy per kilogram, but fission is generally much easier. So all nuclear reactors at the moment use this. The only human use of fusion is in hydrogen bombs. So if you get fission, you get some big nucleus and it splits or fires something out, and that's where the energy comes out. It comes out in the kinetic energy of these things flying apart, and as they fly out they bang into other atoms and cause them to vibrate, and generally causes all the atoms to move faster, which is called heat. So that's how you get the energy out. This breakdown of these heavy fissioning nuclei generates particles that crash into other particles, that gets them moving faster and heats the whole thing up. And this heat can then be used in some sort of heat engine that we've talked about before to generate electricity.